Hi folks, how are you? I hope you are well, that you have a good morning. So today we will continue with the basics of logic design. So we will continue seeing how actually all we have seen at a higher level is implemented in hardware. As always, remember that part of the material of the slides is taken from the book. Okay, so let's continue. Yesterday we showed that there are two types of logic blocks. Remember, combinational logic blocks and sequential logic blocks. The sequential logic ones contain something that we call memory, so they can save values from previous stages. On the contrary, combinational logic blocks do not contain memory, so the output is only going to depend on the input. Okay, yesterday we saw ways for representing those combinational logic blocks. We saw the truth tables, we also saw Boolean algebra and Carnot maps. Today we are going to see how this logical information is implemented in hardware. And for this, we are going to see three components: gates, decoders, and multiplexors. So let's start with the first one, gates. So all logic blocks are built from basic gates. And I'm sure you have heard about those gates and an OR gate, which actually implements the logical and the logical OR we have seen. And we have also the NOT or inversion function, which is also the third element that we have to build logic blocks. So those are the three basic elements for implementing functions: and, OR, and the logical function NOT. Remember that yesterday we saw we saw some representation using Boolean algebra, and those functions, logical functions that we saw yesterday, can be implemented using these three components. Okay, so for the AND gate, we represent it with this symbol. So with this symbol, we mean that we are doing a logical AND operation, and this is how do we represent this element when we design logic circuits. For the OR gate, we have the symbol you see in the screen, and from the inverter or the NOT, the logical NOT function, we have this symbol. Okay, so those three gates or elements are the basics for building more complex logic blocks. So sometimes, in order to simplify the drawings, instead of having, for instance, here I have an inverter, then we have a gate, and then we have an inverter again. So instead of drawing those, explicitly drawing those two inverters, what we usually do is just add these small bubbles, and with this we mean that the input A is inverted. Okay? So this is just a simplification. So this circuit here is equivalent to this one here. It's just for simplifying, okay, for doing it more clear. Similarly, if we want an AND gate inverted, instead of writing an AND gate and then the inverter, we can just have this symbol, and this is equivalent to the one on the left. Okay, in a similar way, we have the inverted OR or an OR gate, which will be the same. It's just adding the bubble there. Okay. So for instance, let's see an example. Yesterday we saw a logic function an equation which was equation D, and it was true if at least one of the input is true. This was implemented with or logical symbols. So we did A or B or C. So what will be the logic gate implementation? What will be the circuit equivalent to this equation? So we will have an OR gate. The input will be A, another input will be B, and this will give us A or B. So the first part of the equation D. And then we will continue. We will add another OR gate, and in this case, what is missing is the input C. So we add here the input C, and finally the output will be D. And this output will be actually A or B or C. Okay? Let's see another example. Now we have equation F, and this logic function is equal to A and B and C, which means that equation F is only true if all the three inputs are true. So in this case, the only changing from previous example is that instead of using OR gates, we are using AND gates. So we will have an AND gate, then we'll have input A, input B, and with this we will have A and B, and then we need to add the third input, which is C. For that we open another AND gate, we add the input C, and finally we have the output F. Okay, makes sense? So let's see an example a little bit more complicated. In this case, we have equation E that it's mixing three inputs, and it's mixing AND logic functions and OR logic functions. So the logic gate implementation in this case will be as follows. So first of all, we have not A and B and C. So here we will have see this bubble. With this bubble, remember, is equivalent to having an inverter here. Okay, so this will be A negated because of the bubble. Then we will have B, and this with this we will have A negated and B. We add another and then we add the input C, and with this we have the first component of this equation, not A, B, and C, which is actually the first part of the equation. Now we need the other two parts. So for the second one, in this case, the value negated is B. That's why we have now the bubble in B for inverting that input. Then we add again the third input, which is C, and add another AND gate, and we have A and not B and not C. With this, we will have this second part of the equation. And now we are going for the third part of the equation, which is A and B, and then we need to negate C. In this case, the bubble is here in the C. We negate it, and we have A and B and not C. And finally, what we need to do once we have the three components of this equation, we need to OR those elements, those components. So in this case, we add an OR gate here for doing the first OR of those two elements of the equation, of those two parts of the equation, and then for the third part, we add another OR gate and just have the final, produce the final E equation E value, which will only be true if exactly two inputs are true. Okay, this is the same equation we saw yesterday, but in this case we have seen the gate implementation. Okay. So now I propose you an exercise. I want you to do something similar, but in this case, I would like that you use this other equation. You implement with logic gates equation F. which says that f is true if c is not true and b is true, which is the first part of the equation, or f is true if a is true and b is not true, which is the second part of the equation. So what will be the logic implementation of this equation? I give you some time. I have no form for this because I have not found any way of checking drawings of logic gates. So I just give you some time and then we review the answer. Okay, the time is over. So now we are going to check the answer. So what we can see here is the following. So first of all, we have B and not C. So for doing this, we then have an AND gate. We negate the input B with the input C, sorry, with the bubble, and then with this gate we have the first part of the equation, B and not C, and then we go for the second part of the equation, which is A and not B. So here we have B inverted, okay, and then we have those inputs, and with this we have A and not B. So we have the first part of the equation and the second part of the equation. And now we need to do this OR here. So we need to OR both parts. So for this, we add an OR part, an OR gate, sorry, and then we have the final output F. Okay, clear? Someone is asking if when we do the OR, an OR function or an AND function, such as in the previous slide here, can we just put the three inputs A, B, and C in a single gate? Yes, you can do that. So it's equivalent to what I'm doing. I'm just doing this because I think that in the beginning it's better to understand. But yes, so those two gates here could be just drawn using one big gate with three inputs. Okay, so that could be perfectly that could be also correct. Okay. Okay, so let's move next to the next hardware I want to show you. So we have seen gates. Now we are going to see something called decoders. So a decoder is we could see it like something for building larger components. So with the gates, we are limited to a small circuits. With decoders, we can use them for building larger components. Actually, decoders and multiplexers, as we will see later, are internally made using gates. So if we have a decoder which has n bit input, an n bit input, so an input of 64 bits or an input of 1 bit, then we will have 2 power n outputs, and only one of the outputs will be true for each input combination. For example, if I have a 1 bit decoder, it will has 2 power 1 outputs. That means 2 outputs. So, and we represent graphically a decoder like this. So in this case, this one here, it indicates that the input is 1 bit. Okay, the input signal here is 1 bit wide, and then we will have 2 outputs, and depending on the output, one of the outputs, only one of the outputs will be true. So what will be, for instance, the truth table for the previous 1-bit decoder? So imagine we have one input and we call that input 10, and then we have 2 outputs, out 0 and out 1. So the truth table will be as follows. So if the input is 0, then that means that the output 0 will be 1 and the output 1 will be 0. So only the output 0 will be true. If the input 10 is 1, only the output 1 will be true. So coming back to the previous draw, so if here this input here is 0, then only this output will be activated, only this output will be 1 and the rest of outputs will be 0. And if the input here is 1, only out 1 will be activated and the rest will be false, will be 0. Okay, so this is what we are actually saying with this truth table. Now, instead of having a 1-bit decoder, imagine I have a 2-bit decoder. That means that we will have 2 power 2 outputs. That is 4 outputs. So then here I will have 2 bits, 2 input bits, and depending on the value of those 2 input bits, one and only one of these outputs will be true. So the truth table for this 2-bit decoder will be as follows. So if the input is 0, 0, only output 0 will be activated. If the input is 0, 1, only output 1 will be activated. If the input is 1, 0, only output 2 will be activated. And if the input is 1, 1, only output 3 would be activated. Okay, going back to the graphical representation. So here I will have 2 bits. If it's 0, 0, only output 0 will be activated. If it's 0, 1, only output 1 will be activated. If it's 1, 0, only output 2 will be activated. And if the input is 1, 1, only output 3 will be activated. Okay, so now I have an exercise for you. So in this case, imagine that we have a 3-bit decoder. So what do you think will be the number of outputs for this decoder? I'm going to add a link to a form, and I'm going to give you a minute to answer this simple question. Okay, time is over. I don't see any responses coming. I don't know if that means that the form is not working or that you need more time. Okay, I see them coming. Thank you. So we have almost all of you think that the answer is 8. So let's see. As we have mentioned, if we have 3-bit inputs, the number of outputs will be 2 power 3, which is actually 8 outputs, as most of you has mentioned. So what will be the graphic representation for this decoder? So as we have mentioned, this graphic representation will be as follows. So we will have a 3 here, indicating that the input is 3-bit wide. Okay, so here we will have, for instance, 0, 0, 0. And we will have 8 outputs. And only one of these outputs is going to be 1, and the rest will be 0. And this will only depend on the 3 bits input. For instance, if the input is 0, 0, 0, I will have this output, this first output, output 0, set to 1, and the rest to 0. If the input is 1, 1, 1, then I will have all the output 0 except for the output 7, which will be set to 1. Okay? So what I ask you now is, what will be the truth table for this 3-bit decoder? So imagine we have 3 inputs called 10, 11, and 12, and 8 outputs called from out 0 to out 7. So in this case, as the form doesn't allow us to have such a table, I have prepared on Canvas, I have prepared a quick quiz there. So if you go there, you will see Lecture 11, Logic Design 2, Exercise 3. So this is a quiz. And yeah, I give you some time for answering this quiz. And yeah, so if it doesn't work, just let me know. Okay, so you have some time to finish this quiz in here, Lecture 11. It's on Canvas. Okay, the time is over. I don't know if some of you have. I see that 12 of you, only 12 of you has answered the question. And according to I see answers coming. In this case, we don't have such a graph, but according to this page, we have 22 respondents and all of you answered it correctly. Okay, so let's see. So it seems it's clear, but just in case. So imagine we have these three inputs, 12, 11, and 10, and then the possible outputs will be, in case all of the inputs are 0, the output will be 1 for the output 0, and the rest will be 0. If only input 10 is activated, then only output 1 is activated. And using this trend, we will have all the possible outputs. I think that this is clear, okay? Depending on the input, only one output will be activated, and as you can see, each time is a different input. So this decoder is just, depending on the input, selects one output, okay? Okay then, so now we have that the decoder, we have one input and we have two outputs. Then we have also something that is the inverse of the decoder, and we call the encoder, which is the inverse of a decoder. So we will have two outputs and it will give us an input, okay? And it's just the inverse of the decoder. It's exactly the same, but inverse. Okay then, so we have seen gates, we have seen decoders, and now multiplexors. Okay, so this is a very important part of combinational logic. So what is a multiplexor? So it works like a selector. In this case, the output is one of the inputs selected by a selector or control value. What that means? For instance, imagine we have a two-input multiplexor. We have two data inputs, A and B. In this case, they are labeled as 0 and 1. And then we have a selector, one selector, which is S. So depending on the value in this selector, the input A or the input B will be selected. So if the selector is 1, the input B will be selected and will be put to the output C. If the selector S is 0, then it will be the input A, which will go through the output C. Make sense? So this signal here, signal S, will select if it's A or B, the signal which goes to output C. Okay. Now we have an exercise similar to the one we have just done, but in this case we are going to do a truth table, but in this case of a two multiplexor instead of the decoder. Okay, so as I have mentioned in the forms, I cannot in the forms I cannot put a table of this size. So as before, I have just prepared a quiz in the Canvas page. Okay, let me show you if I can. I have published it now. So hopefully you can see now. I'm going to show you another exercise. Yeah, I think it's there now. So another exercise, in this case, exercise 4. So I'm going to give you again some time to do this exercise, which is basically as I have in this slide and as you also have in the quiz, the truth table of a two input multiplexor. Okay. This exercise. Okay, the time is over. Let me see if we got some responses. Okay, so here I can see that most of you answered the question correctly. And we are going to see now what was the correct question and why. So, but it seems that most of you has answered this question correctly. Okay, so the truth table for this 2-input multiplexer. So as we have mentioned here, the inputs will be A, B, but also the selector, the input selector, also the signal S. Okay, so in this case, depending on S, we are going to select the input A or B. So the only thing which matters here is S. So if S is 0, such as in the first 4 rows, then we are going to select the input A. It doesn't matter what B is, we are going to select input A. So here C will be equal to A. Okay. On the contrary, if the signal S, the selector, is 1, such as in the last 4 rows, we are going to select B. So C is going to be equal to C, and it doesn't matter the value of A. Okay, makes sense? Okay then. So now that we have the previous input table, so what will be the logic function for this 2-input multiplexer? So I'm going to add a form in the Q&A, okay? And I'm going to give you 1 minute. Yeah, and good luck. Okay, the time is over. Let's see if we have some results. Yeah, we have some responses here. Okay, so most of you got the correct answer. We are going to see actually why that is the correct answer. So we can represent this 2-input multiplexer using the following logic function. So we will have 3 inputs, A, B, and S. So A, B, and S. So in this case, S selects A or B. It selects A if S is 0. So that means if we have A and not S, this will have the value of A if S is 0. Otherwise, this will have 0. Okay, so in here, in this part of the equation of the logic function, this part will be A if S is 0, otherwise it will be 0. And the second part will be the inverse. So in this part, if S is 1, then this part of the equation, the result will be B. Otherwise, S will be 0, and then all this part will be 0. Okay, so this will be the how we represent this two-input multiplexor using Boolean algebra. Okay, and now that we have seen the truth table, we have seen the Boolean algebra representation. So what will be the implementation of this of the previous equation with gates? So in this case, we have two AND and one OR. Okay, so remember that this bubble means that the signal S is inverted, and in this case, this other point means that those wires are connected, so both contain the value of S. It's like a bifurcation. Okay, and this will represent the logic equation we have seen before. So we have input A, S negated, and we do an AND. Then we have input B and input S, and we have another gate AND, and we have an OR gate for all those two parts, and this will give us the final output C. Okay, makes sense? So someone was asking an interesting question. So someone was asking, what if we have, instead of two inputs, A and B, we have three inputs? So how will we choose? How do we choose the input if we only have one selector but we have three inputs? So we are not able of selecting three. We could only select two. So of course, multiplexors data inputs can be wider than 1 bit. So and if they are wider than 1 bit, I will have here more than 1 bit. But what I was referring is for the selector. So I can have multiple selectors here. Okay, I can have n input selectors. So if I have more than two inputs, I will have more than one selector here in order to be able to select all. For instance, if I have two selectors, I can select more inputs from here. Okay, and in the previous slide, what we show is that we can have more than 1 bit here. So this selector can be 1 bit, but we can select input A and input B, and those input can be wider than 1 bit. Okay, so we can have inputs wider than 1 bit, and therefore the output will be wider also, and we can have also multiple selectors here in order to select the values from here. Okay, then now we have the inverse of the multiplexor. So in this case, it's similar to the decoder and the encoder. So the multiplexor is just the inverse of the multiplexor. So in this case, if we have a two-input multiplexor, A, B, and with one selector S, the output will be C. The inverse is what we call the multiplexor, which has an input C, and depending on the value of the selector, selects A or output B. Okay, makes sense? So today we have continued with the combinational logic. We have seen gates, decoders, and multiplexors. And in the next lecture, we will see how to construct a basic arithmetic logic unit with all the gates that we have seen in this lecture and in the previous one. Okay, so now let me check. I think there are some questions here. I'm going to try to address some of them. Okay, someone is asking if I could just explain again the decoder part where we have a 3-bit decoder. Let me check. So here, I think someone is asking if I could repeat this part. So here we have a 3-bit decoder. That means that here the input will be 3 bits, 0, 0, 0, and only one of those 8 outputs will be activated. So if the input is 0, 0, 0, output 0 will be 1 and the rest will be 0. If the input is 0, 0, 1, only input 1 will be 1 and the rest will be 0, and so on. And this is what we have represented in this truth table here. So depending on the inputs of the 3-bit decoder, we will have this output, and only one output will be 1. So in the case that, as I was mentioning, the inputs are 0, 0, 0, the output will be 1 for output 0 and 0 for the rest of outputs. Similarly, if I have input 0, 0, and 1, only output 1 will be 1 and the rest will be 0. So these inputs only select one output. So this decoder means that I have here 3 bits, 1 bit, 2 bits, and only one of the output bits is generated. And this number of output signals depends on the number of input bits. So we have said that the number of outputs in a decoder is 2 power the number of input bits. So in this case, the number of input bits was 3. So the number of outputs, possible outputs, is 8. Okay, hopefully it's clear now. Someone is also asking if it's possible to have extra help outside the class time. So I have mentioned it a lot of times. So you can use the ticket system. That's the best way to reach me and other people which is helping. You can also email me, as some of you are actually doing. I'm always happy to help, but remember, so this is a large, you are a large class, over 400 students, so that's why we have set up the ticket system, in order to be able to provide you a better support. Imagine that if the 400 students email directly to me for help, then it will be difficult to give you support. But if you use the ticket system, it will be easier, because we are more people there in that system. Okay. Let me check if I see any other interested question. Okay, someone is still having questions regarding the decoder. So he's saying, how do you actually know which output should be 1 and which output should be 0? Okay, so let's repeat this again. So the answer to that is actually in this truth table. So here we have all the 3 possible, all the possibilities for these 3 inputs. So we have here in these 3 first columns all the possible values, combinations for the 3 inputs. And depending of those 3 inputs, we are going to select one value. So if the 3 inputs are 0, we are going to select always the output 0. If the 3 inputs are 1, we are going to select always, if the 3 inputs are 0, 0, 1, we are going to select output 1. If the inputs are 0, 1, 0, we are going to select output 2. Okay, it's like incrementing. So if you convert, for instance, this 0, 0, something you could use like a trick. If you convert this 0, 0 from binary to decimal, so 0, 0, 0 will be 0, 0, 0, 1 will be 1, 0, 1, 0 will be 2, 0, 1, 1 will be 3. That you could use that in order to know which output to select. So if 1, 1, 1 converted from binary to decimal, 1, 1, 1 will be 7, which is actually this output selected here. Okay. Someone is asking regarding the exam, if we will be examining on encoders or the multiplexors. For the exam, we will just stay with the basic gates. We will just stay with decoders and multiplexors. I was just mentioning encoders and the multiplexors for completeness, but in the exam we will keep things simple using encoders and multiplexors. But don't worry, you will have, I mentioned it in the previous lectures, so you will have a practice test in the coming weeks, which will show you which kind of questions you will have in the exam. So you will have mock exams to train yourself, and you will know what you can expect in the final class test. So don't worry. And also remember that the last 2 lectures next week, Tuesday and Wednesday, are review lectures, and we will probably be reviewing some of those practice exams in order to be sure that you know what you can expect in the final class test. Okay, let me see if I see any other question. Yeah, someone is asking how we can do with the multiplexer. How can we have all the information if we have discarded part of that information before? Yeah, that's an interesting question. So he's saying, okay, if here I only have C, how do I know A and B? So what actually happens is that I don't need to know A and B, because the selector is going to tell me which output I need to know. So imagine that the selector is 0, then only A will work and C will be A, and B will be doesn't matter what, because it's not going to be used. Similarly, if the selector S is 1, only B will be used, so C will go through B, and A will be discarded, and that's why we don't need the rest of the values. That's why the multiplexor works. Okay, hopefully that is clear now. Another question in the multiple multiplexors. So someone is asking, for selecting between multiple inputs in the multiplexor, do we use multiple selectors or 164-bit selector? So here what we are using is n input multiplexor with 2 selectors. This means we have n input and 2 selectors. Selectors are usually 1 bit, but to be honest, I'm not sure if we can have a selector of more than 1 bit. I think that we use 2 selectors for that purpose, but I will check that, because I'm not sure, because in the book I only see that what can be wider are the data inputs, not the selector, but I will check for that and will let you know in the next lecture. Okay, so thank you very much for your attention. I hope you have enjoyed the lecture. Have a nice rest of the day, and see you tomorrow morning. Okay, bye bye, see you.